Good morning, students. Welcome to the fifth class. So yesterday we have discussed about briefly waveform distortion. Among the waveform distortion, we have seen what is meant by DC offset, its definition, what are the effects of DC offset, and now today we are going to discuss about harmonics. So let us see what is the definition of a harmonic. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the supply frequency, that is fundamental frequency. Okay? Harmonics are nothing but instead of 50 Hz frequency, if there are multiples of supply frequency, that is double the frequency, 100, 150, 200, 250, 300, multiples of the fundamental frequency. These harmonic voltages are known as, these integer multiples of the supply frequency voltages are known as harmonics. Okay? Harmonics are not pure sinusoidal. They are integer multiples of the sinusoidal voltages. The frequency of this harmonics is always greater than that of the integer multiples of the fundamental frequency, that is either even harmonics, either odd harmonics. Even harmonics are 2, 4, 6, 8 of the fundamental frequency, etc. And odd harmonics are 3, 5, 7, 9, etc. of the fundamental frequency. Okay. The major causes of the harmonics are non-linear loads. All the non-linear loads will produce harmonics. The total harmonic distortion is used to measure the effective value of harmonic distortion. So how much is harmonics are present in the given waveform are determined by total harmonic distortion. This is a measure which is used to determine the harmonic content in the given waveform. Okay. The following figure illustrates the waveform and harmonic spectrum for a typical adjustable speed drive input current. Okay. If you see the waveform which is shown here in figure 1, current waveform for an ASD, adjustable speed drive input current. Okay. So if you see the input current, it looks like sinusoidal, but it is not pure sinusoidal. If you observe clearly, it is non-sinusoidal waveform. That means harmonics are present in the given waveform. So what are the different harmonics are present? That is given by the THD, total harmonic distortion. If you see the values which are given in the table, maximum 313.9, minimum minus 171.7, average 33.53, okay? Absolute 313.9, RMS 64.386. Okay. Next, form factor 1.92. Like this. Crust factor CF 4.875. Okay, like this. There are different parameters are shown here. Okay. The ranges of current will vary from around minus 35 to plus 35 approximately. Okay, average is we got 33.3. Absolute value 313. What is RMS value? 64 point, very high value. Because if you see the RMS value is very high, whereas average value is very low. So what is the form factor? Very high, double. Therefore, more distortion in the waveform. Okay, as the difference between average and RMS value is more, the distortion is also more. Okay, this is the figure shows. Actually, only one fundamental sinusoidal waveform should come, but instead of one, here we are getting two fundamental waveforms. Okay, two positive peaks as well as two negative peaks. This comes under harmonics. Here you can see harmonic spectrum for an adjustable speed drive input current. Okay, the same harmonics when you analyze as a spectrum, see that ASD input current spectrum. Okay, for a frequency of 60 Hz, the fundamental component is 19.47, THD, total harmonic distortion is how much? 41%. Okay, so 41% is completely total harmonic distortion. Harmonic content. RMSH 7.9, RMS 21. Okay, like this, if you see. Okay, the bars indicates here the harmonic content at each and every interval, frequency of time. Okay, generally at 600, 300, this is 300, like this. If you see, this is 600, 200, 400, approximately 50 Hz or 60 Hz frequency. You can see what is the total harmonic distortion? Very high. Current is very high. But you can see, this is not only the fundamental, this is the fundamental current. This is not only the fundamental current. We have other currents also, which are present in the given waveform. Next one is interharmonics. Voltages or currents having frequency components that are not integer multiples of the frequency at which the supply system is designed to operate. The supply system generally is designed to operate only at fundamental frequency, either 50 or 60 Hz. But voltages or currents having frequency components that are not integer multiples of frequency at which the supply system is designed to operate are called interharmonics. For example, if it is 50, multiples of integer multiples are 50 or 60, they are called as harmonics. If they are not integer multiples of the fundamental frequency, then they are known as interharmonics. That means, for example, 25, 35, 55, 105. These are all multiples of 50. For example, 185. Okay. Harmonic 15. Like this. These are called as interharmonics. The sources of the interharmonics are static frequency converter, cycloconverters, induction furnaces, arcing devices. These are the four major sources of the interharmonics. Static frequency converter, cycloconverter, induction furnace, arcing devices. Okay. Power line carrier signals can also be considered as interharmonics. So power line carrier signals. Okay. When communication signal is transmitted through the power lines, then that transmission is known as power line carrier. These signals are also considered as interharmonics. Okay, they are not harmonics or they are not fundamental frequencies. They are at different frequencies, which are called as interharmonics. Coming to the fourth point, notching. What do you mean by notching? Notching means there is a small groove, small disturbance, which periodically comes in the waveform. That is called as notching. You can see in the waveform, there are small grooves or small deviations at regular intervals of time in the given waveform. These are known as notching. Okay? Notching is a periodic voltage disturbance caused by the normal operation of power electronic devices when current is commutated from one phase to the other phase. Okay, when current is commutated from one phase to the other phase, R phase is over, next Y phase. Okay, there is a disturbance during the switching time. This is periodic voltage disturbance. This is known as periodic voltage disturbance. Every phase it will come. Okay, R phase, Y phase, B phase, again R phase, Y phase, B phase, like this. This is periodic voltage disturbance caused by normal operation of power electronic devices. Okay, when current is commutated from one phase to the other phase is called as notching. The following figure shows an example of voltage notching from a three-phase converter that produces continuous DC current. The notches occur when the current commutates from one phase to the other phase. During this period, there is a momentary short circuit between two phases, pulling the voltage as close to zero as permitted by the system impedance. Okay, so in between this, okay, commutation, what will happen? See here, the voltage disturbance will occur more, deviations more. This may result in zero voltage also. Okay, when the impedance is more, automatically voltage will become 0 at some instances. Here you can see it's a DC current, DC voltage waveform which ranges from AC current voltage waveform, AC voltage waveform which ranges from plus 500 to minus 500, voltage notching caused by a 3-phase converter. Okay, so the notching is occurring in both positive side as well as negative side. Next, last one is fifth one, notching. So noise. Noise is the unwanted electrical signals with a broadband spectral content lower than 200 kHz superimposed upon the power system voltage or current in phase conductors or found on neutral conductors or signal lines. Noise, you know already, noise. So when power current is flowing through any wire or signal is flowing through any band, you can observe some of the noise. Noise is unwanted electrical signals because when current has to flow, okay, there should not be any noise. But when you observe the outside transmission lines, okay, more noise will come. This is because of so many reasons. We will see now. Okay. Sources of the noises are power electronic devices, control circuits, arcing equipment, loads with the solid state rectifiers, and switching power supplies. Turning on, turning off of the power supply. Loads with rectifiers, arcing equipment, control circuits, power electronic devices, these all will produce noise. Okay, noise is nothing but simply we can call it as unwanted electrical signal, but its bandwidth is very small, that is lower than 200 kHz superimposed upon the power system voltage, okay, or in the phase conductors, or it is found in the neutral, or it is found in the signals lines. The problem can be migrated by using filters, isolation transformers, and line conditioners. Okay, noise can be easily reduced with the help of filters or isolation transformers and line conditioners based on the requirement. Coming to the voltage fluctuation. Voltage fluctuations are systematic variations of the voltage envelope or a series of random voltage changes, the magnitude of which does not normally exceed the voltage range from 0.9 to 1.1 per unit. So fluctuation of the voltage is a systematic variation, continuously will come, systematically. That means, okay, one time small change, one time more change, it will not come. Okay? Throughout the entire time, constant variation in the voltage, which is referred as fluctuation. Okay, of the voltage envelope of the voltage fluctuation are systematic variations of the voltage envelope or a series of random voltage changes, the magnitude of which does not normally exceed the range from 0.9 to 1.1. That means plus or minus 10% to the rated voltage. That is called as fluctuation. That is permissible. That is not very severe. That is negligible. Voltage fluctuations are characterized as series of random or continuous voltage fluctuations. So sometimes continuous fluctuations will come, sometimes random fluctuations will come. Loads that can exhibit continuous rapid variations in the load current magnitude can cause voltage variations that are often referred as flicker. Okay. Flicker is nothing but fluctuation when it is continuous and rapid in the load current magnitude, then it is called as a flicker. Flicker is nothing but a continuous rapid variations on the load side. The term flicker is derived from the impact of the voltage fluctuation on lamps such that they are perceived by the human eye to flicker. Sometimes you can see, okay, when there are voltage fluctuations in our house also, bulb will start flickering. dim, bright, dim, bright, dim, bright. This effect or this phenomena is known as flickering. This is caused by voltage fluctuations. When voltage changes, automatically the glow also will change. That's why it is termed as flicker. To be technically correct, voltage fluctuations is an electromagnetic phenomena, while flicker is undesirable result of voltage fluctuation in some modes. Okay. So voltage fluctuation is nothing but it is an electromagnetic phenomenon, whereas while flickering is nothing but undesirable result of the voltage fluctuations in some loads. Okay, flicker will not occur in every load. For example, if you see TV or refrigerator, etc., we cannot see flickering, but in bulbs we can see flickering. Tube lights also we cannot see flickering. Only in bulbs we can see flickering. The following figure shows voltage fluctuations caused by an arc furnace operation. Okay, here we can see. Continuously you can observe there is continuous changes in the voltages, fluctuations. It should be smooth sinusoidal, but instead of smooth sinusoidal, it is zigzag sinusoidal. This is caused by voltage fluctuations due to different load changes. Okay, this voltage fluctuation caused by an arc furnace operation. Okay? You can observe. And the final one is power frequency variations. The power frequency variations are defined as the deviation of the power system fundamental frequency from its spectral specified normal value. Okay, so it is also one of the variation, but power frequency variation is defined as the ratio of as the deviation of the power system fundamental frequency from its specified nominal value. For example, the frequency is 50 Hz or 60 Hz. If it is changed by a small value, 50.1 or 50.2 or 50.3, etc., the deviation either 0.3 or 0.4 etc., this deviation is called as power frequency variation. Till now I have seen only voltage or current variations, but this is frequency variation. This also comes under power quality problem. The sources of the power frequency variations are nothing but due to faults on the bulk power transmission system, a large block of load being disconnected, or a large source of generation going offline. On modern interconnected power system, frequency variations are rare. Generally, the power frequency variations are very less. Okay, only in some cases, offline. Due to faults on bulk power transmission system, suddenly large transmission power is lost, blocked. A large block of load being disconnected, a large load is disconnected, then automatically there is a drastic change in the power, then it leads to power frequency variation. But nowadays, on a modern interconnected power system, frequency variations are rare. Generally, in the modern interconnected power system, even the large disturbance also cannot change the frequency much. Okay, this is, we'll stop here today. So next class, we are going to discuss about the remaining topics.